Okay, so for this one, okay, so for the part two, chapter two, okay, for the mechanic of materials, the topic that we going to discuss is about the stress and strain under axial loading. Okay, uh, okay, so this is the learning outcome, okay, for this chapter. What we gonna what we gonna discuss is about the axial loading, stress and deformation. Okay. So, what is deformation? Because in the previous chapter, we never consider the deflection or the deformation when we apply the stress or force on the members or beams. Okay. So for the stress and strain diagrams, we're gonna discuss this one. We're gonna learn deformation under axial loading for statically determined structure. So the main thing is the deformation. The symbol is a delta, as well as the statically indeterminate structure. Okay, so what we expect that you can learn is about the how to calculate the stress and deformation. I think you still remember how to calculate the sigma equal to PA. Okay, P is equal to force and E is equal to area, and this from the stress. So that we can calculate the deformations occur during the when we apply a force. Okay, deformation of the bar of the uniform cross section or variable cross section under one or multiple. So uniform cross section is this is the same cross section or area. Okay, variable cross section meaning that different type of bar have a different area. Okay, so we're gonna calculate the stress as well as the deformation, and then calculate stress and deformation of independent bar, redundant support, and composite bar. Actually, this topic is really short actually. Okay, so we can finish by today. Okay, so if you get here that the if we consider the string of the drill pipe, right, suspended from this traveling block on the oil rig, actually is subjected to the extremely large loading, and yeah, it's actually some deformation occur. Okay, although we cannot see, but deformation is occur, but it's going to be written again. Okay, the deformation is going to be elongated, and it's going to return again to the original form. Okay, so you have this one. Okay, so suitable of the structure of machine depends on the deformation in the structure as well as the stress induced under loading. Thus, static analysis alone is not sufficient. So what we have to do is, yeah, static analysis. This is the previous chapter. We do just calculate the force for each member, internal force, what else, and then the axial loading, but we never consider the deformation. Okay, so the determination of the stress distribution within a member also required consideration of deformation in the member, so you have to remember that whether it's going to rupture or not. Okay, so chapter 2 is a concern with the axial loading and the deformation of the structure member under axial load. Okay. While chapter 3 is we gonna deals with the torsional load and angle twist. This one is more to like a gear. Okay. The application. Okay, for the engine. More to like a moment. We use uh, moment knowledge of the moment for the chapter 3. And chapter 4 is we omit from this for this course. Okay. Okay. If you still remember that sigma, okay, axial loading is equal to P divided by A. Okay, is equal to is actually is the stress, and then strain. What you have and what you have to remember is about the to calculate the normal strain. Okay, epsilon equal to delta equal divided by L. So delta is the deformation length of road. Okay, and deformation, and L is the length of road. Okay, how much is going to be deform or elongate this delta. Okay, so if you look at here that if the area is increased or become a double to A, so actually you have to apply um, the force which is a double also. Okay, so that you can get the similar deformations. Okay, but the ratio is the same, still the same. Okay, P divided by A, only you give a double the force is a double. Okay, since the area, the cross section is increased, so to get the same elongates or deformations, so you have to apply double also for the force. Okay, and to calculate the normal strain is similar, the ratio delta divided by L. How about when we increase the length? Okay, the elongation is going to be double to delta. Okay, but the ratio is still the same. Okay, for the stress equal to P divided by A. Since the deformations or elongation is a double to delta, so depending on the length. Okay, but the ratio is still the same. Okay, epsilon equal to delta divided by L. So this is what we get the information about the normal strain. Okay, so for the stress and strain test, okay, I think all of you, I'm not sure if you already conduct the experiment with the what is it, at the thermodynamics and materials engineering laboratory. I think so. I'm not sure. So I think you're gonna use this machine. I'm not sure. Okay, are you going to use or not this machine to test the tensile whether it's going to rupture or not? Okay, the deformation, we can see the deformation here. This machine is used to the tensile test machine. Okay, and this is the specimen test or the sample with the tensile when we try to pull, okay, for both side, okay, at the end of the side. Let's look at here. Okay, when we pull this one, right? So in case for the ductile materials, for example, is characterized by the ability to yield at normal temperature. For example, like steel, alloys, metals. So if you look at here, that the when we increase it, the load, right? Okay, the length also increase. Okay, until sigma y. Okay, so if you look at here that they have a straight line, okay, with the step shape. Okay, this is until sigma y. Okay, and then this one is some the elongation is occur, or neck what is it, the deformation is occur. Okay, so this is the area of the strain handling, and then is the necking. Okay, this is necking. Actually, the if you look at here, there's a like a neck shape. This is the next shape. Okay, this one is the critical value. Okay, and this one is the necking. Okay, this is the necking. So the actually the degree of the necking, actually, look at here, this one, right? Okay, this I think is 45 degree. Okay, 45 degree. Okay, so if you look at here, this is the ultimate strength. Okay, and after this one, after this point, okay, this is the starting to breaking. Okay, if you apply or introduce a very small load, okay, only yeah, very small load, so it's gonna be ruptured. Okay, they have many steps: yields, strength hardening, necking, and then it's rupture. Okay, this is for the materials such as steel, alloy, also metals. However, for the brittles, okay, the brittle materials, this is characterized by the fact that rupture occur without any noticeable change in the range of the elongation. This is the difference actually between the brittles and ductile materials. Okay, for example, cast iron, glass, ceramics. Okay, they have no the graph, which is yield and or strain hardening, is become rupture. Okay, for the brittle strain at the time of rupture is much smaller than for ductile materials. Okay, so this is the difference between brittle as well as ductile materials. Okay, so let's see the deformation under axial loadings. How can we determine the deflection or deformation of the materials when we apply the force? Okay, if we consider the Hooke's law, okay, this one sigma equal to EA. E is a modulus young or modulus elasticity. So if we substitute to the if we rearrange, okay, we can get for the epsilon or norm or the strength, okay, equal to sigma divided by E. So sigma is equal to P divided by A. Okay, this one. And then what we get is from the definition of the strain, okay, delta divided by L. Okay, so just substitute to the left side. Okay, this one here. So we can get delta L equal to PA divided by PA E. Okay, and then you rearrange this equation, we can get solving for the deformation. How to get this deformation? Okay, delta equal to PL divided by AE. So this one is only for the homogeneous root. For example, this one. So this is homogeneous. This is homogeneous. How about if you have many shapes like this one, right? Which is non-homogeneous. Okay, how to calculate this one? Okay, so you have to calculate based on this equation, which is with variation in loading and cross-sectional of the or material properties. So that means variation in loading, number one, cross-section, different cross-section and different material. For example, you have this one is the metal and this one is the cast iron. Okay, so you have to calculate by using this one summation of each deformation or each section. Okay, so you have to remember this is the main thing that you have to highlight. Okay, so let's see the sign conventions as well as the which direction. If you look at here that when the constant external force is applied at each end of the member, sigma equal to PL divided by AA. This is for the homogeneous rod or materials. Look at here, this is the deflection. If you pull to this side and pull to this, maybe this one is the fixed point. Okay, so different direction but same magnitude. Okay, so this is the deflection, and the sign convention is negative for the compression. Okay, and a negative for the compression and positive for the tension or elongation. So this is a positive, this one is positive, but if to this direction, which is compression, okay, so it should be negative. Okay, so any question about that, about the main equation for the deformation based on the hooks? Any question? Any question? Okay, so if you have no questions, let's we see the examples. Okay. So if you look at here, that determine the deformation of steel rod, okay, shown under the given. Good. So if you look at here, that they have a difference loading as well as different cross-sectional area. Okay, and it's given the modulus yang for the materials. So the material is the same. Okay, what for this rod bar. Okay, which is steel rod for both section. Okay, So what you have to do is you have to draw free body diagram. Okay, this is important, and you have to use method of section. Okay, to determine the deformation for the steel rod. Okay. So for the procedure, what you have to do is divide the load into component at the load application point. Okay. For examples, okay, what you have to do is you have to do cross section. This part first, and then okay, you have to cut to this part. Okay, and then you have to cut this part. Okay, small, big, and bigger. Apply a free body analysis on the each component to determine the internal force, method of section, and then you have to evaluate the total component deflection. So the total component deflection summation, okay, equal to sigma I Pi Li divided by Ai for each and divided by E. Since E is the same, okay, same, just is given the modulus Young for the steel rod, okay, same material they use, only different in cross section as well as load given. Okay, so if you look at here, okay, so what we have to do, this one, right? Same, right? This is what I told you. Okay, so this is the actually is the main and the original figure. Okay, I think you have to do like this one. First you have to draw this one. Okay, and then you have to cut which within any section between point C to D. Okay, so this one they cut between just in the middle. Okay, so this the arrow on the right side, and similarly also this one is P3. Okay, opposite direction but same magnitude. Okay, and then second is you have to cut between point B to C in order to determine P2. Okay, so this similarly also, so you remember this one, they have a force also introduced here, and this one is force, meaning that this one is a two force. Okay, similarly also for point A to B, this is for this one. Okay, so you have to cut. Okay, and then if you look at here, okay, we have to determine for all force, each force. Okay, so PCD, this one is P3. See, we use the method of section. This one is P3, and then PBC, this one P2, and this one is PAB, P1. Okay, just opposite direction. So if you look at here, that this one is similarly also negative. If you do what is it, the total fx, right, equal to zero in equilibrium. Okay, so PCD negative PCD plus the T equal to 0. So you can get PCD positive. Okay, that is all for the determination for force for each section. Okay, and then once you determine force, okay, you have to evaluate total deflection. Okay, so if you look at here, that the total deflection is the same since use the same materials. PAB is you substitute here, PBC, right, for each section, and the length of if you look at here, LAB, the length is what is it, 12. Okay, L1 is equal to L2. Okay, and then CD, LBC. LBC is also, this one is 12. Okay, BC, and then another one is C, 16. Okay, so and the area. Okay, and you can get total deflection for the road. Okay, I think it's easy. Okay, this is the first examples. Okay, look at the second example. Okay, so if you look at here that for the second example, determine the internal force for each segment and the displacement of NA. NA is here. NA just at the end of alpha AD. Okay, and then assume 3-meter bar is made of the steel and its segment is equally divided. Cross section area is 1 square meter. So it's easy this one because it's the same material. Okay, so if you look at here, similarly also you have to use the method of section. You have to use I think the 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 easiest thing is you have to draw the the original crossbar. Okay, and then you do the method of section. Okay, and then this one similarly also. Oh, this one. Okay. So and then you calculate PAB as well as PAB. What else? You have to calculate. And then PBC. Okay. And should be PCD similarly with the end of the point D. This one is in compression, BC in compression and AB in tension. Okay. So if you look at here that compression should be negative. Okay. So and this displacement at the point A, okay, A with respect to point D, okay. So this one is the ratio means A respect to the point D, D as a fixed point, okay. Okay, so for each sections, okay, you have to get the total displacement, okay. Just substitute all the force length as well as area. E is the similar because only the what is it steel. Okay, so we can get the displacement of an A with respect to D. Okay, so with respect to D, we do assumption that this point as a fixed point. Okay, okay, respect to D. So the main thing is you have to know how to cut in which section. Okay. For example, this one you have to consider you have to cut within point A and B. And this one you have to cut within the point B to C and then C to D. Okay, this one C to D. Okay, just in the middle. Okay. So the displacement of A and A with respect to D, okay, we can get, okay, positive delta means move away from D, which is elongate or positive, okay, tension, and negative move toward the D, which is shorten, okay. Double subscript indicate relative displacement. This is what I told you, okay. Single subscript displacement is to be determined relative to the fixed point. So if D is a fixed support, displacement is denoted as delta A. So this is what the meaning of this one. The meaning of that one is point D is the fixed point, is the fixed support, tap on the wall. Okay, so you just do displacement at point D. Okay, but D subscript point D A D. So this is a respect to point D. We do assumption that point D as a fixed support. Okay. Okay. Any question about these two examples? If not questions, I think uh, the main tutorials or example is for the example 3. This is quite tricky, which is you need the knowledge of trigonometry. Okay. So if you look at here, actually we want to find the deflection at point point D, but we have no information for the bar C, CD. Okay, since we apply force at the point E. If you look at here that the rigid bar BDE is supported by two links, AB and CD, right? Link AB is made of aluminiums. Okay, this one, AB. Okay, this one is different materials. And then has cross sectionals, okay, 500 square millimeter. Link CD is made of steel. Okay, this one is steel, different materials. Okay, and this one is aluminium. Okay, that's why it's different modulus yang. Has cross sectionals 600 square millimeter. The force 30 kilonewtons. Okay, this one. Okay, apply at point E. Okay, determine the deflection at point B. You can determine D, this one. Okay, as well as point E. How to determine the deflection at point E? Okay, this one. Okay, it's quite difficult because there's no information here. Okay, so what you have to do is you have to know the knowledge of trigonometry. Okay, so first apply free body analysis to the bar BDE. Okay, first is bar BDE, this one. So you have to isolate all the bar, and then you have to analyze force AB and then also force CD. So bar BDE is the number one. Second, you have to analyze AB, and then third, you have to analyze bar CD. After that, you can determine the deflection for the point E. And then evaluate the deformation point link of AB, DC, this one also, and displacement of B and D. Work out the geometry to find the deflection F at E given the deflection at B and D. Geometry. 1, 2, 3, trigonometry. Okay, so if you look at here that free body diagram for the BDE, okay, just based on your sense, how to put the arrow for the force FAB and FCD. Okay, since we apply force here at point E, so maybe when you apply going up, this one also going up. Okay, just based on your sense. And if you look at here that they have two unknowns here. Okay, two unknowns AB as well as CD. Okay, so the method that you have to use is for the equation of equilibrium is the moment. If that is the best equation that you can use rather than you use Fx as well as Fy. Okay. Okay. So first we determines by using a moment at point B equal to 0, so that we can reduce the number of unknown and become to only one. So we can get FC CD. Okay. So you can determine FC CD. Okay. And then after that, by using also a method of the moments. Okay, moment at point D. Okay, so we can get the FA AB. Okay, negative 60. Okay, and then second is we have to analyze displacement of point B. So we have to analyze road AB. Okay, since we know that the FAB is negative, okay, meaning that it is a compression. Okay, so if you look at here that negative 60, just analyze the deflection at the point for the bar AB, so we can get the deflection. Okay, similarly also we have to analyze for the bar D, okay, which is the displacement of the point B, so that we can get 0.3 millimeter. Okay, the displacement, it should be in meter or millimeter or centimeter. Okay, because it's this displacement or deformation, right? So it should be this unit, okay, or inch. Okay, so FCD is tension. Okay, it is a tension. So that the value is positive. Yeah. Okay. So since we determine the displacement at the point E and as well as a point D, okay, the next step is the main step, which is you have to find the displacement at the point E. Okay, if you look at here, since this one they have no bar, okay, how can we analyze the deflection at the point E, right? Okay, so what we have to do is we do the method of ratio, okay, or geometry. So if you look at here that BB divided by BH, okay, and then we can get also DD divided by DH. If you rearrange, we can get this equation. Okay, so this one it should be here. It should be here. But if you rearrange, it's become to this one. Since we want to make it similar. Okay, DD equal to HD. This one DD and BB. Right, same right. And HD is similar with the BH. Okay, so if you look at here that BB, okay, BB is the deflection at the point B from the previous this one from the previous slide. This one deflection at point B. This one is deflection at point D, DD. Okay, BB and DD. This one is BB. This one DD. This is the deflection. Okay, so just substitute to this equation. Okay. Similarly, also for BH and HD. Unfortunately, if we make a equation here, this length is equal to the total is, if you look at here that from point B to point D, the length is the length is 200 millimeter. So if we what is it? Note here as a x as the distance. So this is should be 200 minus x. Okay. So just substitute here for the BH, which is 200 millimeter minus x. This is the total length, 200 millimeter. Okay. And then divide by x, since HD is equal to x. So we can get x equal to 73.7 millimeter. Okay. Similarly, also with the knowledge of the geometry, okay, EE, look at here, EE, right, HE, DD, and HD. Okay, this green, dark green with the blue, okay, light blue. Okay, just make the ratio so that we can get deflection for the point E. So since EE is the deflection point E, okay, substitute for the DD is a 0.3, okay, 400 plus with the X, okay, because the total length is 400 plus with X, okay, the total length from H to E, and divide by 73.7, this is X, this one is X, so that we can get deflection for the point E. Okay, delta E equal to 1.922 to 1.928 millimeter. Okay, so this is the kind of equation that I will prepare for the final equation. So you have to master this type of the method or how to use the ratio or geometry. Okay, you have to remember this one. Okay, okay, okay. Any question about this example 3? Any questions? How to use method of the trigonometry or geometry? Actually, the rest is a tutorial. Okay, I think you can read by yourself. I don't need to explain because the solution is already there. Right. Any question
Doc
about? Yeah.
Doctor, I have a question, but not regarding the trigonometry, the previous one.
Which one?
The
This one.
yeah, this one.
Yeah.
So for P, we insert the value of, I mean, like for compression it's negative.
Yeah.
Oh, okay.
Okay. The compression is negative. Just this one, since it's negative, but if you want to present your result, you replace with the arrow. so negative is there, disappear. Okay, so if you look at here, the arrow is towards up up here, right? So that means it's compressed to this bar. So that's why we remove the arrow to represent as compression, or you can write as a compression, and then you can remove the negative. Okay, so this one is already tension is positive because we get this one based on your initial sense, right? You imagine this one is maybe your, because this one you analyze for the road BDE, but for the road AB your analysis is going to be opposite this 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 direction or tension. FAB is a tension, but actually is compression. Okay, so you have to correct this arrow, right? For AB become this direction. Okay, this direction. Look at here, that's why this one is compression. Okay, so meaning that your arrow for the bar BDE, it should be this direction. Okay, so that's why we include the negative. But if you want to remove negative, you have to put sign C here or arrow to up or down. Okay, so that we can remove the arrow. Okay, do not forget about that. This is showing that either the bar is in compression or tension. Okay, any questions? Any more? Okay, if you have no question, okay, as I told you, it's a very short chapter. Okay, sorry for yesterday because I have a meeting. Okay, it should be we can finish yesterday actually. Okay, just I would like to highlight for the tutorials. Okay, for the tutorials, one is I think it's almost similar. Okay, you have to read how to find the deformation for delta AB as well as BC. Okay, this one is a direct. I mean, there's a no. You don't have to do the trigonometry. It's similarly like example one as well as example two. So you have to cut at any section between AB and also BC, so that you can get the deformation for the AB and also BC. Okay. Yeah, total deformations. Okay. And then this one is a tutorial too. I would like to highlight this one. Okay, you have to read this one carefully. This is similar, just like tutorial three, example three. Okay, how to determine the deflections, which is by using a trigonometry or geometry. Okay, I think so you have to read this one. Okay, I already provide the solution, right? And the rest you can do the tutorials. Even the last chapter I still not provide the tutorials. I will provide after this. Okay. So any question before we stop for this subject? I don't think so we can discuss this one. Any questions? No more questions. Okay. If no more questions, I think it's clear. Okay, your task is to read tutorial 1 to 3. Okay, this is important. Okay, especially for tutorial 2. Okay, if you don't understand, you can ask me. Okay, in the next class. Okay, maybe it's possible. Okay, yeah, it's possible. We can discuss, but you have to read first and do the tutorials for chapter 1 and chapter 2. I will provide by today after this class. Okay, it seems like my explanation is clear. Okay, so what I would like to highlight is for this chapter is the determination of the deflection as well. Yeah, deflection as well as the from the normal strain as well as the stress. Okay. Similarly, also for the chapter 3 actually. Okay, for the chapter 3,